Interstellar travel sounds simple. You leave Earth, cross the darkness, and reach another star. But space is not empty in the way we imagine. It is distance. Distance so vast that even light needs years to cross it. The nearest star system is more than 4 light years away. That means the fastest thing in the universe still takes years just to reach our closest neighbour. And for a spacecraft, it becomes something far worse. Energy becomes impossible. Time becomes impossible. Radiation becomes deadly. And every tiny particle in space becomes a bullet. This is not just a journey. It is a fight against physics itself. Welcome to Falling into Space. And if you're ready to understand why reaching the stars may be harder than humanity ever imagined, don't forget to subscribe, because tonight, we're not just looking at the stars, we're asking if we can ever truly reach them. You look up at the stars, and they feel close. Tiny lights scattered across the sky, silent, beautiful, still. It feels like if humanity became advanced enough, if we built a powerful enough engine, if we waited long enough, we could simply go there, leave Earth, cross the darkness, reach another sun. But the moment you begin to measure the distance, the dream starts to break. Because space is not just large, it is almost impossible to understand. The moon feels far from Earth, but light reaches it in just over 1 second. A spacecraft can reach it in a few days. Mars feels distant, but at the right moment, a mission can get there in months. Jupiter is far deeper into the solar system. Saturn is farther still. Neptune sits so far away that sunlight takes more than 4 hours to reach it. But all of this is still local. All of this is still our neighbourhood. The real wall begins when you try to leave the solar system. Because the nearest star is not just a little farther than Neptune, it is thousands of times farther. The closest star system to us is Alpha Centauri, and even that is more than 4 light years away. That means light itself, the fastest thing in the universe, takes more than 4 years to cross the gap, and light travels at about 300,000 kilometers every second. Every second. Now imagine a spacecraft. Even the fastest spacecraft humans have ever built move at speeds that seem incredible by Earth standards. But compared to the distance between stars, they are almost motionless. At those speeds, reaching the nearest star would not take years. It would take tens of thousands of years, longer than recorded human history, longer than civilizations, longer than languages, longer than nations. A spacecraft launched today toward the nearest star would arrive so far in the future that the people who built it would be ancient history before it even crossed a fraction of the distance. This is the first problem with interstellar travel. Distance does not scale the way our imagination wants it to. On Earth, distance feels conquerable. A far country can be reached in hours. A continent can be crossed in a day. The ocean, once impossible, became a route. But space is different. There is no road, no refueling station, no repair stop, no air, no protection, no margin for error. Between stars there is only distance and time becomes the enemy. Because even if you build a spacecraft that can survive for centuries, what about the people inside it? A human life is short. Too short for the stars. If the journey takes thousands of years, then the spacecraft is no longer a vehicle. It becomes a world, a sealed artificial civilization drifting through darkness. It must carry food, water, energy, medicine, spare parts, knowledge, and generations of human life. It must survive without Earth, without resupply, without rescue, and every system must keep working, not for months, not for years, for centuries, maybe longer. That is not just engineering, that is almost a planet in miniature. And even if you solve the problem of time, another problem appears immediately. Speed. To make interstellar travel possible within a human lifetime, you would need to move at a significant fraction of the speed of light. Not airplane speed, not rocket speed, not even the speed of our fastest probes, something far beyond what we can currently achieve. But accelerating a spacecraft to those speeds requires energy, an enormous amount of energy. And the heavier the spacecraft is, the worse the problem becomes. A small probe is difficult, a human spacecraft is far harder, a city-sized generation ship is almost unimaginable. Because every kilogram matters, every piece of metal, every shield, every person, every drop of water, every storage system, every machine. All of it must be accelerated, and the faster you want to go, the more energy you need. At low speeds, the challenge is already massive. At near-light speeds, it becomes extreme. Physics does not care how much you want to reach the stars, it charges the full price, and the price is energy. Now imagine you somehow solve that. You build an engine powerful enough to accelerate a spacecraft to a fraction of light speed. You have only solved half the problem, because once you get moving, you must eventually stop. Reaching another star is not the same as flying past it. If you cannot slow down, you do not arrive. You only pass through the system at incredible speed, seeing your destination for a brief moment before disappearing back into deep space. So you need fuel not just to accelerate, but to decelerate, and that means carrying even more fuel. But carrying more fuel makes the spacecraft heavier. A heavier spacecraft needs more energy. More energy means more fuel. And the cycle grows worse. This is called the tyranny of the rocket equation. It is one of the most brutal truths in space travel. The more you carry, the more you need to move what you carry, and the more you need to move it, the more you must carry again. This problem becomes especially painful when your destination is not a nearby orbit, but another star. A journey so long that every inefficiency becomes enormous. And then there is radiation. Space between stars is not completely empty. It is filled with cosmic rays, high-energy particles, and radiation from distant sources. On Earth, our atmosphere and magnetic field protect us. Inside the solar system, the sun's influence provides some structure. But in interstellar space, protection becomes far harder. A spacecraft traveling for decades or centuries would need shielding. Thick shielding, heavy shielding, but shielding adds mass, and mass makes acceleration harder. Again, physics closes the trap. You need protection to survive, but protection makes the journey harder, and if you travel faster, the danger becomes even worse. Because at a large fraction of light speed, even tiny particles become deadly. A grain of dust is no longer harmless, it becomes a high-energy projectile. A speck of matter drifting in space could strike the spacecraft with enough force to damage or destroy critical systems. At normal speeds, dust is a nuisance. At interstellar speeds, dust becomes ammunition. The empty space between stars is not a perfect vacuum. There are atoms, particles, microscopic grains. Not many, but over light years of travel, even rare collisions matter. A spacecraft moving near light speed would be flying into a storm of invisible hazards. Every impact carries energy. Every particle becomes dangerous. The faster you go, the more violent the universe becomes. So speed solves time, but creates impact. Slowness avoids some danger, but creates centuries of travel. Every solution becomes another problem. And this is why interstellar travel is so difficult. It is not one obstacle. It is many obstacles stacked on top of each other. Distance, time, energy, fuel, energy, radiation, dust, life support, repair, navigation, deceleration. Each one is difficult alone. Together they become something far beyond ordinary space travel, and still, we have not even reached the destination. Because arriving at another star does not guarantee safety. The nearest stars may have planets, but that does not mean they are habitable. A world may orbit in the right zone, but still be hostile. Too much radiation, no atmosphere, locked in eternal day and night, bombarded by stellar flares, frozen, dry, toxic, dead. After travelling for thousands of years, you may arrive at a system that cannot support life at all. And then what? You cannot simply turn around. You cannot easily choose another star, because every star is separated by another impossible distance. Interstellar travel is not like sailing between islands. It is more like crossing an ocean so vast that there may be no land at the other side, only another darkness. This is the reality behind the dream. The stars are not just far away. They are separated from us by physical limits that cannot be ignored. A science fiction story can skip the journey. A movie can cut from Earth to another star in one scene. But the universe does not cut. The universe makes you cross every kilometre, every second, every danger, every consequence. And that is why the first step toward understanding interstellar travel is not building an engine, it is understanding the scale. Because once you understand the scale, you understand why the stars have remained out of reach for all of human history. Not because we lacked imagination, not because we lacked ambition, but because the space between stars is designed by physics to be almost impossible to cross. And yet, the stars are still there, still shining, still calling. And that is what makes the problem so powerful. Humanity can see destinations it may never reach. We can measure them, name them, study them, imagine worlds around them. But reaching them is something else entirely, because between us and the nearest star is not just space. It is the full weight of physics, and this is only the beginning. Even if humanity decides to go anyway, even if we accept the distance, the time, the danger, and the uncertainty, the next question becomes simple. How do you actually move a spacecraft across interstellar space? This is where the dream becomes even harder. Because leaving Earth is already difficult. Every rocket launch is a battle against gravity. Every spacecraft must carry fuel, structure, engines, instruments, and protection. Even reaching orbit requires enormous energy. But orbit is close. The Moon is close. Mars is close. Compared to the stars, the entire solar system is still only the starting point. To cross the gap between stars, ordinary rockets are almost useless. Chemical rockets are powerful enough to leave Earth, but they are not efficient enough for interstellar travel. They burn fuel quickly, produce thrust for a limited time, and then the spacecraft coasts. This works for missions inside the solar system because planets are close enough and gravity assists can help. But for another star, this is not enough. A chemical rocket cannot simply keep accelerating for years. It would need impossible amounts of fuel. The fuel itself adds mass. More mass requires more fuel. More fuel adds more mass again. The problem grows until the idea collapses under its own weight. So you need something else. A better engine. A more powerful energy source. And this is where the most ambitious ideas begin. Nuclear propulsion is one possibility. Instead of chemical reactions, a spacecraft could use nuclear energy to heat fuel and push itself forward more efficiently. This could be much better than ordinary rockets, but still not enough for easy interstellar travel. It may reduce the problem, but it does not erase it. Then comes fusion. Fusion is the same basic process that powers stars. If humanity could build a fusion engine, it might produce far more energy than chemical rockets. In theory, a fusion-powered spacecraft could reach higher speeds and make the journey to nearby stars shorter. But the word shorter is dangerous. Shorter does not mean easy. Even with advanced fusion, the journey could still take decades, centuries, or more depending on speed, mass, and design. The ship would still need to carry fuel, it would still need shielding, it would still need to slow down at the end, and fusion itself is extremely difficult to control. On Earth, we are still learning how to make fusion useful as a practical energy source. Turning it into a reliable spacecraft engine that works for decades in deep space is another level entirely. Then there is antimatter. Antimatter is one of the most powerful energy sources imaginable. When matter and antimatter meet, they release energy with incredible efficiency. In theory, antimatter propulsion could provide the kind of power needed for serious interstellar travel. But in practice, antimatter creates problems almost as large as the journey itself. It is extremely difficult to produce. It is extremely difficult to store. It cannot touch normal matter because if it does, it annihilates. A spacecraft carrying antimatter would need magnetic containment systems that never fail. Not once, not for a second, not across years or decades of travel. And the amount of antimatter needed for a large human mission would be far beyond anything we can currently produce. So again, the idea is powerful, but the reality is brutal. Another idea is a light sail. Instead of carrying all the fuel, a spacecraft could use a huge reflective sail pushed by light. A powerful laser from Earth or orbit could push the sail forward, accelerating it to very high speeds. This is attractive because it avoids carrying massive amounts of fuel, but it creates a different problem. The spacecraft must be extremely light. That works for tiny probes but not for humans. A small chip-sized spacecraft could possibly be pushed to a fraction of the speed of light. A giant ship carrying people, equipment, food, water, and shielding would be far harder. And even if you accelerate with a laser, you still need to slow down when you arrive. If you cannot decelerate, you only fly past the star system. A journey lasting decades or centuries could end in a few hours of observation. That is not settlement. That is not arrival. That is a flyby. So every propulsion idea faces the same truth. You can choose one problem to reduce, but another problem grows. If the ship is small, it can go faster, but it cannot carry people. If the ship is large, it can support life, but it becomes harder to move. If you go slowly, the journey takes too long. If you go fast, radiation and dust become deadlier. If you carry more fuel, you need more energy. If you carry less fuel, you may not be able to stop. There is no simple path. Physics does not give you a shortcut for free. Now imagine that somehow you build an engine that works. A true interstellar engine. It accelerates your spacecraft to a meaningful fraction of light speed. Maybe 10%, maybe 20%. Suddenly the nearest stars are no longer tens of thousands of years away. Now they are decades away. Still long, but possible within a human lifetime. At first, that sounds like victory. But then relativity enters the story. At high speeds, time itself begins to behave differently. For the people inside the spacecraft, time may pass slightly slower than it does for people back on Earth. At extremely high speeds, this effect becomes stronger. This is called time dilation. Science fiction often treats this as a solution. If you travel close enough to light speed, the journey might feel shorter for the travelers, but it creates a strange cost. When you arrive, Earth may have aged far more than you have. The people who launched you may be gone. The civilization that sent you may have changed completely. The language, politics, technology, even the reason for the mission, all of it may be different. You might reach another star and realize that you no longer truly belong to the world that sent you. And that is assuming communication still matters, because communication between stars is painfully slow. Even a message traveling at light speed takes years to cross interstellar distances. If you send a message from Alpha Centauri to Earth, it takes more than 4 years to arrive. Then Earth replies, another 4 years. A simple conversation takes almost a decade. There is no real-time control, no emergency support, no quick instructions. Once the spacecraft leaves, it must be independent, completely. If something breaks, Earth cannot help in time. If the crew faces a decision, they must make it alone. If the destination turns out to be dangerous, there may be no rescue. Interstellar travel is not just travel, it is separation. A mission to another star is not like sending astronauts to the moon. It is not even like sending humans to Mars. Those are hard, but they remain connected to Earth. Interstellar travelers would cross into a different kind of isolation. A silence measured in years. Now think about navigation. Across the solar system, spacecraft can use planets, radio signals, star trackers, and ground control to correct their paths. Small errors can be fixed over time, but in interstellar travel, small errors become enormous. If you're traveling for decades across light years, even a tiny mistake in direction can grow into a massive miss. You may not pass near the star at all. You may arrive millions of kilometers away from where you needed to be. And when your target is another star system, precision matters. You need to enter the system at the right angle. You need to avoid dangerous regions. You need to slow down. You need to find stable orbits. You need to identify planets, hazards, radiation zones, dust, debris, and gravitational interactions. All of this must happen after a journey so long that the original mission plan may be outdated before arrival. The spacecraft must be intelligent enough to adapt. Not just automated, but deeply autonomous. It must survive without constant human support. It must diagnose problems, repair systems, adjust course, protect its passengers, manage energy, handle emergencies, and keep doing this for years or generations. Now imagine a generation ship, a spacecraft so large that people live, grow old, have children, and pass the mission to the next generation before reaching the destination. This solves the problem of human lifespan. But it creates a new problem: society. You're no longer designing a vehicle. You're designing a closed civilization. It must maintain culture, education, food production, medical care, governance, mental health, and cooperation across generations. A machine can be engineered. A society is far harder. What happens if people no longer believe in the mission? What happens if systems begin to fail? What happens if population grows too fast or too slowly? What happens if knowledge is lost? What happens if the destination becomes irrelevant? The ship must remain stable not for one crew, but for many lifetimes, and all of this inside a sealed artificial environment surrounded by radiation, darkness, and distance. This may be one of the hardest parts of interstellar travel. Not the engine, not the fuel, but keeping a living civilization alive in a metal world between stars. Then there is the question of biology. Humans evolved on Earth, under Earth gravity, with Earth's day-night cycle, Earth's magnetic field, Earth's atmosphere, Earth's microbial environment, Earth's oceans and ecosystems. Remove all of that, and the human body begins to change. Muscles weaken in low gravity, bones lose density, radiation damages cells, isolation affects the mind. Artificial gravity might help, but it requires spinning structures or constant acceleration. Both add complexity, both add mass, both add failure points, and failure points are deadly in deep space. A small problem on Earth is repairable. A small problem in interstellar space can become permanent. There is no spare planet nearby. Now, even if the ship survives, even if the people survive, even if the engine works, even if the navigation is perfect, there is one final question. Why go? Not why dream, not why explore, but why physically send humans? Because robots can go first. Small probes are easier to accelerate. They need no food, no water, no air, no artificial gravity, no society. They can be tiny, fast, and disposable. If interstellar travel ever begins, it will almost certainly begin with machines, not humans. Tiny probes pushed by lasers, robotic explorers, signals sent back across the dark. Human bodies are heavy. Human needs are complex. Human missions are harder by every measure. So the first true journeys to the stars may not carry people at all. They may carry instruments, cameras, sensors, small machines that cross the darkness because they can survive what we cannot. And this reveals something important. Interstellar travel may not be impossible in every form, but human interstellar travel may be physically and practically close to impossible. The universe allows the idea. Physics does not forbid movement between stars, but it makes the cost so high, the risk so large, and the requirements so extreme that the dream becomes almost unreachable. Not because the stars are protected by walls, but because the gap between them is enough. Distance becomes the wall, energy becomes the lock, time becomes the price, and every possible solution demands something greater than anything humanity has ever built. This is why interstellar travel remains one of the most powerful dreams in science. It is visible, it is imaginable, it is mathematically possible, and still, it remains almost beyond reach. Because between Earth and the stars there is no enemy, no monster, no barrier you can destroy. There is only physics, and physics does not move aside. Even if the engine works, even if the ship is fast enough, and even if the route is perfect, another problem begins the moment the journey becomes long enough. The spacecraft must become its own planet, not symbolically, literally. Because Earth is not just the place humans live. Earth is the system that keeps humans alive without us thinking about it. It recycles water, it produces oxygen, it grows food, it protects us from radiation, it stabilizes temperature, it gives us gravity, it gives our bodies a natural rhythm. A spacecraft traveling between stars would have to replace all of that, inside a sealed machine, for years, or decades, or centuries. And this may be one of the most impossible parts of interstellar travel, because a rocket can fail once and the mission is over. But a life support system must not fail at all. It must work every day, every hour, every second. It must recycle air perfectly. It must keep carbon dioxide under control. It must clean water again and again. It must grow food without soil from Earth, without natural sunlight, without open weather, without ecosystems that evolved over billions of years. And it must do this while surrounded by deep space. No resupply, no rescue, no backup planet. On Earth, if one farm fails, another can feed people. If one machine breaks, another can replace it. If one city loses power, help can come from somewhere else. In interstellar space, there is nowhere else. Everything you need must already be on the ship. Every tool, every spare part, every medicine, every seed, every system, every possible solution. And that creates a strange problem. To survive the journey, the ship must carry more equipment, but more equipment adds mass. More mass makes the ship harder to accelerate. The harder it is to accelerate, the more energy you need, and the more energy you need, the harder the mission becomes. So survival itself makes the journey more difficult. A small probe can cross space because it does not need comfort. It does not need food. It does not need sleep. It does not panic. It does not get sick. Humans do. And that changes everything. Now imagine the ship itself. A spacecraft designed for interstellar travel cannot be fragile. It cannot be like a modern satellite that works for a few years and then stops. It must last longer than almost anything humans have ever built. Not just survive launch, not just survive space, it must survive time. Metal weakens, electronics degrade, radiation damages circuits, moving parts wear down, seals leak, sensors drift, software fails, dust accumulates. Small problems become large problems when no one can replace the entire system. And across a journey of decades or centuries, even tiny failure rates become dangerous. A 1 in a million failure sounds safe. But if millions of parts are working for thousands of days, probability starts to become an enemy. Something will break, something will need repair, something will behave in a way no one predicted, and the crew must be ready. But what if the crew is not engineers? What if several generations have passed? What if the people repairing the ship were born inside it and have never seen Earth? What if the mission has become a story told to children, instead of a memory held by the people who launched it? That is where interstellar travel becomes more than physics. It becomes culture. A generation ship would not just need engines and walls, it would need education, laws, language, trust, purpose. It would need a society strong enough to survive inside a closed world where mistakes cannot be escaped. If conflict happens on Earth, people can move away. Countries have borders, cities have distance, there are resources spread across a planet. On a ship there is no outside. Every disagreement happens inside the same sealed environment. Every crisis affects everyone. If food production fails, everyone suffers. If oxygen systems fail, everyone is in danger. If leadership collapses, there is no second society waiting nearby. The ship becomes humanity reduced to one container. And that container must remain stable longer than many civilizations have lasted on Earth. This is a terrifying thought, because history shows that societies change, beliefs change, goals change. People forget why things began. A mission launched with hope could become a prison for descendants who never chose it. Imagine being born on a ship between stars, told that your entire life exists for a destination you will never see. Your children might see it, or their children, or no one if something goes wrong. Would people still believe in the mission? Would they maintain systems they do not fully understand? Would they preserve knowledge perfectly? Would they trust the original plan? Or would the ship slowly become its own world, with its own politics, its own fears, its own myths? The physics of interstellar travel is brutal, but the human part may be even harder. And then there is the body itself. Humans are not made for deep space. We are Earth creatures. Our bones expect gravity, our muscles expect resistance. Our hearts, blood, lungs, balance, sleep, and immune systems all evolved under one planet's conditions. Remove that environment and the body begins to change. In low gravity, bones lose density, muscles weaken, fluids shift, the heart adapts, balance becomes strange. The body survives, but it does not remain unchanged. For a short mission, this can be managed. For years, it becomes harder. For generations, it becomes a biological experiment. One solution is artificial gravity. You spin the spacecraft, creating a force that feels like gravity. But spinning a structure large enough for humans adds engineering problems. It must be huge, stable, balanced, and strong. If it rotates too quickly, people feel sick. If it rotates too slowly, it must be enormous. Again, the solution adds mass, and mass is always the enemy. Another solution is constant acceleration. If the ship accelerates steadily, passengers feel gravity-like force. But maintaining constant acceleration requires incredible energy and fuel. Then you must reverse and decelerate for the second half of the journey. Elegant in theory, almost impossible in practice. So the ship must either create gravity with structure, accept biological damage, or invent something far beyond current technology. None of these are easy. Now consider radiation again, but not as a single danger, as a lifetime environment. On Earth, the atmosphere and magnetic field protect life from much of space radiation. In interstellar space, that protection is gone. A spacecraft must shield its passengers constantly. Radiation does not need to destroy the ship instantly to be dangerous. It can damage cells slowly, increase cancer risk, harm reproduction, damage embryos, affect nervous systems, weaken health across generations. To protect against it, You need shielding. Water can help. Thick material can help. Magnetic fields might help. But all of it adds complexity. And if you are protecting a whole human habitat, the shield must be large. Large means heavy. Heavy means harder to move. Once again, survival fights against speed. Then there is food. A ship cannot simply carry enough packaged meals for centuries. It needs agriculture. But agriculture in space is not simple. Plants need light, nutrients, water, carbon dioxide, stable temperatures, and protection from disease. They need pollination or controlled reproduction. They need genetic diversity. They need systems to prevent collapse. On Earth, farming depends on ecosystems far larger than the field itself. Soil contains life. Air moves naturally. Water cycles. Sunlight arrives for free. In space, every part of farming must be engineered. Every photon of light must come from energy. Every drop of water must be recycled. Every nutrient must be recovered. Waste must become resource. Death must become fertilizer. The ship must imitate a living planet in miniature. And if that ecosystem fails, the mission fails. This is why closed life support systems are so difficult. Nature works because it is massive, redundant, and self-correcting across huge scales. A spacecraft is small, fragile, and artificial. It can be designed carefully, but it cannot easily replace the complexity of Earth. And the longer the journey lasts, the more every imbalance matters. Too much bacteria, too little oxygen, a crop disease, a nutrient shortage, a water contamination problem, a failed algae system. Any one of these could threaten the entire population. Now imagine the psychological side. The ship is enclosed. There are no open skies, no oceans, no forests, no natural horizon, no weather, no true outside, only walls, machines, corridors, recycled air, artificial light, and the knowledge that beyond the hull is vacuum. For a few months, humans can endure confinement. For years, it becomes harder. For lifetimes, it becomes reality. How does the mind respond to a life without Earth? How does a child develop after being born inside a machine? How does a society stay healthy when every person lives under permanent dependence on technology? The ship must not only keep bodies alive, it must keep meaning alive, and that may be harder than building engines, because humans need purpose, they need beauty, they need connection, they need variation, they need a world. A generation ship would have to create not just survival, but life worth living, and that is a much bigger challenge. This is where interstellar travel begins to feel physically possible, but practically impossible. The laws of physics may allow matter to travel between stars, but carrying a living human civilization across that distance requires solving nearly every problem at once. Energy, shielding, food, water, air, gravity, medicine, repair, governance, education, psychology, reproduction, navigation, deceleration. And every solution must last longer than the people who designed it. That is the true difficulty. Not just reaching another star, but remaining human on the way there. Because the journey does not only test machines, it tests whether life from one planet can survive without that planet. And that question is far darker than it first appears. Maybe we can send probes. Maybe we can send machines. Maybe one day we can send small robotic explorers to nearby stars and receive their signals years later. But sending humans means taking Earth with us, not the whole planet, but enough of it to keep us alive. And the more you understand what Earth provides, the more impossible that becomes. Interstellar travel is not just a journey across distance. It is an attempt to escape dependence on the only world that ever made us possible. And that is why the stars remain so difficult. Not because they are hidden, not because they are unreachable in imagination, but because to reach them alive we must become something we have never been before. A species that can carry its own world through the dark. The deeper you think about interstellar travel, the more one problem rises above all the others. Speed. Not just moving fast, not just building a better engine, but facing the hardest limit in the universe, the speed of light. Everything in space seems to invite motion. Stars shine across the darkness, galaxies drift through the void, planets orbit, comets fall, light crosses unimaginable distances, but underneath all of that motion there is a rule, a boundary. Nothing with mass can reach the speed of light, not because we lack technology, not because we haven't tried hard enough, but because the structure of physics itself does not allow it. The closer an object with mass gets to light speed, the more energy it needs to accelerate further. At first, this sounds manageable. Add more power, build a stronger engine, use a better fuel. But near light speed, the requirement grows without limit. The spacecraft becomes harder and harder to accelerate. Every extra increase in speed costs more energy than the last. And to actually reach light speed, the energy required becomes infinite. That is not an engineering problem, that is a physical wall. This means that any real spacecraft, no matter how advanced, must travel slower than light. Maybe much slower. And once you accept that, the universe becomes painfully large again. The nearest stars are still years away even for light. For a physical spacecraft, they are longer. Always longer. This is why science fiction creates shortcuts. Warp drives, wormholes, hyperspace, jump engines. Because without shortcuts, the story becomes trapped by distance. But the real universe does not offer shortcuts easily. A warp drive sounds simple in imagination. Instead of moving through space faster than light, you bend space itself. Compress space in front of the ship, expand space behind it, and let the ship ride inside a moving bubble. In theory, this avoids breaking the rule directly. The ship is not locally moving faster than light. Space around it is changing, but the problem is not the idea, the problem is the cost. To create a warp bubble, you may need forms of energy that we do not know how to produce or control. Concepts like negative energy or exotic matter appear in the mathematics, but not as tools we can simply collect and use. The equations may allow a shape, but that does not mean nature allows the machine. There is a huge difference between something existing in mathematics and something being physically buildable. A bridge can exist in a drawing. That does not mean the materials exist to hold it up. And even if such energy were possible, controlling space-time itself would require precision beyond anything humanity has ever approached. You would not be building an engine. You would be shaping the geometry of reality around a spacecraft, across interstellar distances, while keeping the people inside alive. The idea is beautiful, but the universe does not become easy because the idea is beautiful. Then there are wormholes, a tunnel through space-time, a path connecting two distant regions, allowing a traveller to cross a cosmic distance without moving through all the space between. Sounds like the perfect answer. No long journey, no thousands of years, no need to cross every kilometre. But again, physics becomes difficult. A wormhole, if it exists, would likely be unstable. It could collapse before anything passes through. Keeping it open may require exotic matter, the same kind of strange requirement that appears in warp drive ideas, and even if a wormhole could be held open, there is another problem. Where does it lead? You cannot use a wormhole to reach another star unless one end already exists near that star. If both ends are not already positioned, you still need to move one end across space. Which brings you back to the original problem: distance. A shortcut is only useful if you can place the doorway where you want it. And placing the doorway may require the journey you are trying to avoid. There is also the problem of causality. Faster than light travel is not just about speed. It threatens the order of cause and effect. In relativity, space and time are connected. If information or objects can travel faster than light, some observers may see events happen in reversed order. A message could arrive before it is sent. A journey could create paradoxes. This is not just philosophical. It is built into how physics understands time. The speed of light is not only the speed of light, it is the speed of causality, the speed at which influence can travel, the maximum speed at which one event can affect another. So when you try to go faster than light, you're not only trying to beat distance, you're trying to break the structure that keeps time ordered. This is why the light speed limit matters so much. It is not an arbitrary cosmic speed limit. It is part of the way the universe protects consistency. Now imagine trying to ignore all shortcuts and simply go fast but still slower than light. Suppose you reach 10% of light speed. That is already incredibly fast. At that speed, Alpha Centauri becomes reachable in several decades. Not easy, but no longer tens of thousands of years. But the faster you travel, the stranger the journey becomes. The stars ahead begin to shift in appearance. Light becomes compressed in front of you. Radiation becomes more intense. The universe itself seems to change because of your speed. The empty darkness ahead is no longer passive. It becomes an environment you're colliding with. Even individual atoms in interstellar space become high-energy impacts. They are rare, but over years of travel, rarity stops protecting you. The spacecraft must endure constant exposure to particles arriving with enormous energy. At these speeds, the front of the ship becomes one of the most important parts of the mission. It must protect everything behind it. It must absorb or deflect impacts. It must survive erosion. It must handle radiation. It must do this for years without failing. And if the shield is damaged, there is no repair yard ahead. No emergency station, no rescue vehicle. The ship is alone. Now consider navigation at these speeds. In the solar system, if you're slightly off course, you can correct. You can fire thrusters, you can adjust gradually. But at interstellar speeds, corrections become more expensive and more dangerous. A tiny error grows over distance. A small mistake in direction, repeated across light years, can turn into a massive miss. You are aiming not at a nearby target, but at a moving star system years away. The star is moving, the planets are moving, the spacecraft is moving, everything is in motion, and the information you have is always old. When you observe a star 4 light-years away, you see it as it was 4 years ago. For farther stars, the delay becomes greater. The universe you navigate is not the universe exactly as it is now. It is the universe as light has revealed it. So your navigation must predict the future position of your destination, not just where it appears, but where it will be when you arrive. And if the journey takes decades, everything must be calculated far ahead. Now imagine arriving. Arrival is not a single moment. It is another impossible phase. You must slow down from a fraction of light speed. You must do it without burning more fuel than you could carry. You must enter the system safely. You must avoid dust, asteroids, radiation, and unknown gravitational interactions. You must identify a safe path. If the spacecraft is robotic, it must do all this autonomously. If it carries humans, it must protect them during the most dangerous part of the journey. The beginning is difficult. The middle is lonely. The ending may be the hardest part. Because arriving at another star means entering an unknown system after a journey too long for quick correction from Earth. Every decision must happen locally. Every problem must be solved there, and if the system is not what you hoped, the mission has no easy alternative. There is no second nearby target. Another star may be years away. Another journey. Another impossible distance. This is why interstellar travel is not simply about building speed. It is about building certainty in an environment where certainty is almost impossible. You need to know the destination is worth the journey. You need to know your ship can survive. You need to know your systems can last. You need to know your arrival plan will work, but space does not guarantee any of that. Now think about communication again, but on a deeper level. A spacecraft heading to another star becomes more isolated every second. At first, messages take minutes, then hours, then days, then months, eventually years. A question sent from Earth may not be answered for nearly a decade if the ship is near the closest star. For farther missions, communication becomes almost symbolic. Not conversation, not control. Only delayed signals crossing the void. This changes the meaning of exploration. On Earth, explorers can report back. Space missions can receive commands. Even Mars rovers can be guided slowly from home. But an interstellar mission cannot be managed from Earth in real time. It must become independent, and independence means risk. The mission must continue even if Earth changes, even if funding disappears, even if the people who launched it are gone, even if the civilization that receives the message is not the same civilization that sent the ship. Interstellar travel stretches not only distance, but history. A mission to another star is a message sent into the future, and the future may not answer. Now the central truth becomes clearer. The stars are visible because light can travel. But visibility is not reachability. Seeing something does not mean you can go there. The universe allows us to observe across distance far more easily than it allows us to cross distance physically. A telescope can receive ancient light. A spacecraft must pay the cost of motion. That difference is everything. Astronomy makes the universe feel open. Physics reminds you it is not. We can see galaxies billions of light years away, but reaching even the nearest star is beyond anything we can do. This is one of the strangest truths of human existence. We can know things we may never touch. We can map places we may never visit. We can understand stars better than we can reach them, and maybe that is why interstellar travel feels so powerful, because it sits at the edge between imagination and reality. It is not obviously impossible in every form. A small probe might one day cross the gap, a signal might return, a tiny machine might glimpse another star system. But humans, large ships, colonies, civilizations moving between stars, that remains something far heavier, something that demands not one breakthrough but many. Energy beyond anything we use today. Materials that survive extreme impacts, shields that can endure radiation for decades, autonomous systems that never fail, closed habitats that function like planets, and perhaps new physics that may not exist. This is why the phrase physically impossible does not mean the stars are magical or forbidden. It means that under the physics we understand, useful interstellar travel fights against the deepest limits of nature, the limit of light speed, the cost of energy, the danger of motion, the delay of communication, the fragility of life. Every path forward narrows, every solution creates another barrier, and still the stars remain above us. Bright, silent, unreachable. Not because they are hiding, but because the universe placed them behind distances so vast that even light takes years to cross. And for anything slower than light, those distances become a wall. Even if humanity somehow crosses the distance, survives the journey, protects the ship, keeps people alive, and reaches another star, the hardest truth may still be waiting at the destination. Because arriving near another star does not mean finding a new home. It only means you have reached another system, and a star system is not automatically friendly. From Earth, distant planets can look full of promise. We detect them as tiny shadows passing in front of stars, or as slight gravitational movements in the light of their suns. We measure their size, estimate their mass, calculate their orbit, and sometimes place them inside what scientists call the habitable zone. That phrase sounds hopeful. Habitable zone. It makes the mind imagine oceans, skies, clouds, maybe even green landscapes beneath an alien sun. But the habitable zone does not mean a planet is habitable. It only means the planet is at a distance where liquid water could exist under the right conditions. Could, not does. And the right conditions are everything. A planet may sit perfectly in the habitable zone and still be dead. It may have no atmosphere, or too much atmosphere. It may be frozen solid, or covered in runaway heat. It may be blasted by radiation. It may be tidally locked, with one side facing its star forever, and the other side trapped in endless night. It may have violent weather, toxic chemistry, unstable gravity, no magnetic field, or a surface that cannot support anything living. From far away, we may only know that it is there, not that it is safe, and this changes the meaning of interstellar travel. Because the journey is not just difficult, the reward is uncertain. Imagine spending centuries crossing the darkness, only to arrive at a planet that looked promising from Earth, but turns out to be impossible. The atmosphere is wrong, the pressure is wrong, the star is unstable, the surface is frozen, the radiation is deadly, there is no easy backup plan. You cannot simply choose another planet nearby. Even inside the same system, worlds may be separated by enormous distances. And if none of them are usable, the next star is another impossible journey away. So the spacecraft must arrive prepared for disappointment. It must be able to survive even if the destination fails. That means it cannot depend completely on finding a habitable world. It must already be a habitat, a mobile world, a sealed environment capable of continuing even after arrival. This makes the mission heavier, more complex, and more difficult again. Because the ship is not just transportation, it is insurance against the universe being empty of welcome. Now think about the stars themselves. Not all stars are like the Sun. Many of the closest and most common stars in the galaxy are red dwarfs. They are smaller, cooler, and can live for incredibly long periods of time. At first, this sounds good. Long-lived stars give planets more time, but red dwarfs can also be violent. They can release powerful flares, bursts of radiation that may strip atmospheres from nearby planets or make the surface dangerous. And because red dwarfs are cooler, their habitable zones are much closer to the star. That means any planet warm enough for liquid water may orbit very close enough to become tidally locked, one side always facing the star, the other side always facing darkness. A world like that might still have livable regions near the boundary between day and night. Maybe. But that is not the same as Earth. It is not a comfortable second home waiting in space. It is a fragile possibility, a narrow zone of survival, and even if such a planet has an atmosphere, that atmosphere must survive billions of years of stellar activity. It must have the right gases, the right pressure, the right temperature balance, the right chemistry, the right protection. The number of conditions required for Earth-like life is enormous. We often talk about finding Earth 2.0, but Earth is not just a planet at the right distance from a star. Earth is a whole chain of conditions working together. A stable orbit, a long-lived star, a protective atmosphere. A magnetic field, liquid water, plate tectonics, a carbon cycle, a large moon that stabilizes tilt. A history without too much destruction. A surface chemistry that allowed life to begin and continue. Change one part, and the outcome can be completely different. Venus is close to Earth in size. Mars is close enough to imagine. Both are uninhabitable. That is the warning. A planet can look familiar in one way and be completely hostile in every way that matters. Now, imagine arriving at an alien planet after the journey. Before anyone lands, the spacecraft must study it. Atmosphere, radiation, surface temperature, gravity, weather, orbit, magnetic environment, chemical composition, possible toxins, potential biological risks if life already exists. Because another living world would not automatically be safe. If alien life exists, it may not be compatible with humans. It may not be dangerous in a dramatic way, but its chemistry could be unpredictable. Microorganisms, unknown organic compounds, or environmental interactions could create risks that cannot be understood from orbit alone. And if the planet has no life, that is not automatically better. A lifeless planet may require total construction. Habitats, power systems, air production, water extraction, food growth, radiation protection, temperature control, medical systems, repair facilities, everything. You do not land and begin a new civilization. You land and begin fighting the environment. Again. Only this time, Earth is not nearby. There are no supply ships coming soon. No emergency return. No global economy behind you. No planet full of factories and specialists in spare parts. The colony must build from what it has, or fail. This is where colonization becomes harder than travel. A spacecraft can survive as a closed system for a mission, but a colony must grow. It must become self-sufficient. It must produce materials, not just consume them. It must mine, refine, manufacture, repair, educate, heal, and reproduce across generations. That means the destination must provide resources, not just beauty, not just land, useful resources, water, metals, carbon, nitrogen, energy, accessible minerals, stable conditions, and even if those resources exist, they must be reachable with the tools the travelers brought. A planet may contain everything needed deep underground, but if the colony cannot access it, it might as well not exist. A world may have water locked in ice, but extracting and purifying it requires energy. A world may have metals, but refining them requires industry. Industry requires machines. Machines require parts. Parts require manufacturing. Manufacturing requires more machines. This loop is difficult even on Earth. In another star system, it becomes extreme. A true interstellar colony would need to carry the seed of an entire technological civilization. Not just people, not just shelters, but the ability to rebuild tools, create new parts, and maintain knowledge. Without that, the colony slowly becomes simpler. Machines fail, technology declines, capabilities shrink. And the dream of reaching another star becomes a slow return to survival. Now think about communication with Earth after arrival. Even if the mission succeeds, a message home takes years to arrive. If the destination is farther than the nearest stars, it could take decades. A discovery made today might not be known on Earth until years later. A question sent back might not receive an answer for half a lifetime. The colony is effectively alone, emotionally alone, politically alone, scientifically alone. It may still remember Earth, but it cannot depend on Earth, and over time that separation becomes cultural. The people born there may not think of Earth as home. They may see it as origin, history, myth, a place their ancestors came from, not a place they belong to. This is another hidden cost of interstellar travel. The moment humans truly leave for the stars, humanity begins to split. Not by country, not by language, but by distance so large that connection becomes symbolic. A human civilization around another star would evolve separately. Its problems would be different, its environment different, its priorities different, even its sense of time different. And if many colonies existed across many stars, there would be no single human future. Only scattered islands of humanity, separated by years or centuries of communication delay. No central control, no shared present, only distant signals crossing the dark. This may be the real form of interstellar civilization if it ever happens. Not an empire spreading between stars, not fast travel, not ships moving freely from system to system, but isolated worlds, each one alone, each one carrying a piece of humanity forward. And that is if everything works, if the destination is useful, if the ship survives, if the people survive, if the colony can grow, if the environment does not destroy them, if the star remains stable, if the resources are enough. Every if matters, because unlike missions inside the solar system, failure cannot be corrected easily. A Mars mission can be planned with launch windows, resupply, communication, and possible return. An interstellar mission has no such safety net. It is a one-way commitment into uncertainty. And this is why reaching another star is not the same as becoming interstellar. A single probe could fly by, a single ship could arrive, but a true interstellar civilization would need repeated travel, reliable transport, stable colonies, resource networks, communication systems, and the ability to survive independently across deep time. That is not one invention, it is an entire new stage of existence. A stage where humans are no longer a planetary species, but also not truly free of planets. Because even in another system, life still needs a world, or something that replaces one. And replacing a world is almost impossible. This is the great contradiction. We dream of interstellar travel because we want to escape the limits of Earth. But to survive the journey, we must recreate Earth. Inside ships, inside habitats, inside colonies. Everywhere we go, we carry the same needs: air, water, food, gravity, protection, community, meaning. The stars do not remove those needs, they make them harder to satisfy. And so the destination, which feels like the hopeful part of the story, becomes another wall. A star may be reachable in theory, a planet may exist, a signal may return. But a home is something much rarer. A world where humans can live without endless artificial support may be incredibly uncommon. May be rare enough that the nearest one is not 4 light years away, not 10, not 20, maybe hundreds, maybe thousands. And if that is true, then the distance problem becomes worse than we imagined. Because reaching the nearest star is not enough. You must reach the right star, the right planet, the right conditions, the right future, and the universe does not promise that nearby. That is what makes interstellar travel feel physically impossible in practice, not because every piece violates physics, but because every required condition stacks on top of the next. The ship must be possible, the journey must be survivable, the destination must be useful, the colony must become independent, the people must endure, the systems must last, the environment must cooperate, and none of these are guaranteed. The stars are full of worlds, but most worlds are not homes. Most are too hot, too cold, too dry, too violent, too irradiated, too unstable, or simply too unknown. And after crossing the impossible distance, that may be the hardest truth to face. The universe may not be empty, but it may still be almost impossible to live in. So the dream continues. We look up. We imagine ships crossing the dark. We imagine new skies, new suns, new worlds. But beneath the dream is the same quiet reality. Reaching the stars is not enough. You must survive what waits there. And what waits there may not want you at all. Even after all the engines, all the shielding, all the habitats, and all the possible destinations, there is still one problem that feels almost unfair. Interstellar travel does not only challenge science, it challenges civilization itself. Because a journey to another star is not something one generation begins and finishes easily. It is not a mission like building a space station, sending a probe, or landing on the moon. It is a project so large that it may need to outlive governments, economies, cultures, and even the people who first believed in it. And that creates a question that is rarely asked. Can a civilization stay focused long enough to reach another star? The stars demand patience on a scale humans are not naturally built for. We think in years. Governments think in election cycles. Companies think in profit cycles. Families think in lifetimes. But interstellar travel thinks in centuries. Even if the spacecraft is robotic, even if it is small, even if it does not carry humans, the mission may still take decades or longer. The people who launch it may not be alive when it arrives. The scientists who designed it may never see the results. The civilization that receives the signal may be very different from the one that sent it. That means the mission requires faith in the future. Not religious faith, civilizational faith. A belief that the people who come after you will still care, that they will still listen, that they will still have the technology to receive the message, that they will still understand the purpose of what was sent into the dark. This is not a small requirement. Human history is full of broken plans, forgotten projects, lost languages, collapsed systems, and abandoned dreams. A mission to another star would have to survive all of that. It would need archives that do not vanish, institutions that do not lose interest, communication systems that remain usable, and a culture that still values a signal arriving from a machine launched generations earlier. In that sense, interstellar travel is not only an engineering problem, it is a memory problem. Can humanity remember a mission long enough for it to matter? Now imagine a probe reaching another star after 50, 100 or 200 years. It takes images, measures planets, detects atmospheres, maybe finds something extraordinary. Then it sends the data home, but the signal is weak. Extremely weak. It spreads across space as it travels, becoming thinner and harder to detect with distance. Earth must have receivers ready, pointed in the right direction, listening at the right time using compatible systems. If those receivers no longer exist, the discovery passes through space unheard. The mission succeeds physically, but fails historically. That is a strange kind of tragedy. The spacecraft arrives, the science happens, the signal crosses the dark, but no one catches it. This is why interstellar missions need not only spacecraft but continuity, a chain of care across time, and continuity is one of the hardest things civilizations can maintain. Now consider the cost. A true interstellar mission would require resources on a scale unlike anything currently built. It would need energy systems, manufacturing capacity, deep space infrastructure, navigation networks, communication arrays, and materials that can endure extreme conditions. For humans, it would require far more. A ship large enough to carry life, a closed habitat, shielding, redundancy, food production, medical systems, long-term repair capability. All of that costs energy, materials, labour and time, and every society must decide what it is willing to spend those things on. On Earth, there are always urgent problems: food, water, climate, war, disease, infrastructure, poverty, energy, security. A civilization may dream of the stars, but it must survive at home first. And this creates another uncomfortable truth. Interstellar travel may require a civilization so stable, so wealthy, so technologically advanced, and so united in purpose, that it is difficult to imagine from where we stand now. Not impossible, but distant. Because the project does not end when the ship launches. It must be supported before launch, during travel, during arrival, and during communication afterward. It is not one heroic moment, it is a long commitment, and long commitments are fragile. Now imagine trying to build the infrastructure. A laser sail mission, for example, might require an enormous energy system capable of pushing a tiny spacecraft to a fraction of light speed. The laser must be powerful, precise, and stable. It must track the sail carefully. It must avoid destroying the spacecraft. It must operate with extraordinary control. That is only for a small probe. For a larger ship, the scale becomes far greater. If the spacecraft uses nuclear or fusion propulsion, fuel must be produced, stored, and handled safely. If it uses antimatter, the production challenge becomes almost absurd. If it uses a generation ship, the construction challenge becomes closer to building a moving city than a spacecraft, and all of it must be tested. But how do you fully test an interstellar ship? You cannot simply run a complete practice mission to another star. The test is almost as hard as the mission itself. You can test engines, you can test habitats, you can test shielding, you can simulate systems, but the full journey only happens once, and if something fundamental was missed, the failure may not appear until the ship is already far beyond help. This is another reason interstellar travel feels so unforgiving. The distance removes the ability to fix mistakes. On Earth, engineering improves through failure. Machines break, people learn, designs change. In interstellar space, failure may happen too far away, too late, and with no possibility of repair from home. The first mission must be closer to perfect than almost anything humans have ever built. And perfection is not how technology usually develops. Now think about the universe itself. It is not a friendly ocean waiting to be crossed. It is mostly empty, but not empty enough to be safe. It is dark, but filled with radiation. It is quiet, but filled with time. The danger is not always dramatic. It is not always explosion or impact. Sometimes the danger is simply duration. A system that works for 10 years may not work for 100. A material that survives one environment may slowly degrade in another. A society that begins with purpose may lose that purpose. A habitat that is balanced at launch may drift out of balance slowly. Interstellar space does not need to attack you. It only needs to wait, and time will do the rest. This is why the dream becomes heavier the longer you think about it. At first, interstellar travel feels like a question of speed. Then it becomes a question of energy, then survival, then destination. But finally it becomes a question of endurance. Can anything we build last long enough? Can anything we plan remain meaningful long enough? Can anything human stay stable across the distances between stars? Maybe the first answer is not to send humans at all. Maybe the realistic future of interstellar exploration begins with machines, tiny probes, intelligent systems, small instruments pushed to extreme speeds, carrying no life, no habitat, no society, only sensors and memory. That kind of travel is still difficult, but it is far more realistic. A machine can be small, a machine can sleep, a machine can endure silence. A machine does not need gravity or food or emotional meaning. It can cross the dark in a way humans cannot. But even then, it must send something back, and that signal must be received. So even robotic interstellar travel still depends on civilization lasting long enough to listen. This may be the most honest form of our first step to the stars. Not colonization, not humans walking under another sun, but a tiny machine passing through another system, collecting a few moments of data, then whispering across light years, a faint message from the edge of possibility. And maybe that message would change everything. Maybe it would show another planet, another atmosphere, another ocean, maybe even signs of life. But it would also remind us of the truth. We can look farther than we can go. We can learn from distances we cannot cross. We can touch the stars with information before we ever touch them with bodies. And perhaps that is where interstellar travel begins, not as migration, but as knowledge. Still, the human dream remains, because humans do not only want data, we want presence, we want to stand somewhere, to see it with our own eyes, to feel that we have arrived. But the universe does not care about that desire. It allows light to travel. It allows matter to move. But it does not make the journey easy for living things. That is the quiet cruelty of the stars. They are visible enough to inspire us, but distant enough to resist us. They feel close in the night sky, but they are separated by gaps so large that human ambition becomes small beside them. And yet maybe that is why the dream survives. Because impossible things have always pulled humanity forward. Not because they were easy, but because they revealed the limits of what we were. Interstellar travel may remain physically impossible for humans in the way we imagine it now. No fast ships, no simple colonies, no easy path between suns. But the attempt to understand it teaches us something important. It shows us how rare Earth is, how fragile life is, how powerful physics is, and how enormous the universe truly is. The stars are not just destinations, they are measurements of our limits. And every time we look at them, we are reminded that the universe is not built around human timescales, human bodies, or human dreams. It is older, larger, colder, and far less forgiving. So if humanity ever reaches another star, it will not be because the journey became easy. It will be because we changed what it means to travel. Maybe we send machines instead of people. Maybe we send frozen embryos, digital minds, or self-replicating probes. Maybe we learn to build habitats that last longer than nations. Maybe we discover physics that changes everything. Or maybe we never go. Maybe the stars remain forever visible, forever studied, forever imagined. but never reached by human footsteps. And if that is true, then interstellar travel is not a failure of imagination. It is a reminder of reality. Some distances are not meant to be crossed casually. Some dreams require more than courage. Some journeys ask for a civilization stronger, wiser, and longer lived than anything we have ever been. And until then, the stars will remain exactly where they are, bright above us, silent beyond us, calling, but not waiting. And now, after every problem has been opened, one truth becomes impossible to avoid. Interstellar travel is not difficult because we lack courage. It is difficult because the universe is built on scales that do not care about courage. The stars are not far in the way a mountain is far, or an ocean is far, or another planet is far. They are far in a way that breaks the meaning of distance. They are separated from us by gaps so enormous that even light, moving at the fastest speed possible, needs years just to reach the nearest one. And everything slower than light must pay an even greater price. A spacecraft can be designed, an engine can be imagined, a mission can be planned. But every idea eventually meets the same wall. Time, energy, mass, radiation, isolation, and the speed limit of the universe. No matter how advanced humanity becomes, these are not ordinary obstacles. They are not problems that disappear just because technology improves. They are built into the structure of reality itself. This is why the dream feels so painful. Because the stars are visible, they are not hidden. Every night they are right there, scattered across the sky, shining with a quiet invitation that feels almost personal. They make distance look harmless. They make the galaxy look open. They make travel feel like destiny. But seeing is not reaching. A telescope can cross the universe with light. A spacecraft must cross it with matter, and matter is heavy. Matter needs energy. Matter can be damaged. Matter must obey limits. This is the difference between astronomy and travel. Astronomy lets us receive the universe. Travel demands that we enter it, and entering it is far harder. Maybe one day, small machines will do it. Tiny probes, lighter than anything that could carry a human, pushed by powerful beams of light, might cross the distance to another star. They may pass through a distant system, take a few images, measure an atmosphere, detect a magnetic field, or glimpse a planet under another sun. Then they may send a faint signal back, a whisper across years of darkness. And perhaps, long after the people who launched them are gone, that signal will reach Earth. Maybe it will show us an alien world. Maybe it will show us oceans, maybe clouds, maybe nothing. But even if that happens, it will not mean humans have crossed the stars. It will mean our instruments have. That matters. But it is not the same, because the human dream is not only to know, it is to arrive, to stand beneath a different sky, to feel sunlight from another star, to look at a horizon no human has ever seen before and say, "We came here." That dream is powerful. But it may be one of the hardest dreams our species has ever created. Because to carry humans to another star, we would need to carry a piece of Earth with us. Not symbolically, physically. Air, water, food, gravity, protection, medicine, repair, culture, memory. A spacecraft for humans would not be a vehicle. It would be a world in motion. A tiny artificial planet trying to survive in a place where planets are separated by impossible darkness. And the longer the journey lasts, the harder that becomes. Every system must endure. Every mistake grows. Every failure matters. There is no outside help, no emergency landing, no second chance waiting nearby. Between stars, survival becomes absolute. Either the ship works, or it doesn't. That is the cruelty of interstellar space. It does not attack like a storm. It does not move like a predator. It simply waits. And time becomes the danger. Time weakens machines. Time tests societies. Time erodes purpose. Time turns mission plans into ancient documents. Time turns the destination into a promise that only descendants may see. And if the journey takes generations, then the people who arrive are not the people who left. They are not explorers in the normal sense. They are the children of a decision made before they were born. They did not choose Earth. They may never see it. They may know it only through recordings, stories, and old images of blue oceans under a yellow sun. For them, the ship is home. The mission is inheritance. And that raises a question deeper than engineering. Is it fair to create generations whose lives exist only to complete a journey? Is survival enough if the destination belongs to someone else? Can a civilization remain human inside a closed machine cut off from every natural world? These are not easy questions, and they show that interstellar travel is not only a matter of physics, it is also a matter of meaning. Because a journey between stars changes what humanity is. If we ever leave the solar system for good, we do not simply expand, we divide. A colony around another star would not share the same present as Earth. Messages would take years, decades, maybe centuries. News would arrive late, decisions would be made alone, culture would drift, language would change, history would separate. There would be no single human civilization moving together. There would be islands, distant, independent, slowly becoming different from one another. That may be beautiful, or lonely, or both. And still, the physical problem remains. Even after arrival, another star system may not welcome us. A planet may look promising from far away, but close up it may be frozen, toxic, unstable, irradiated, or dry. It may have no air, no water, no protection, no usable resources. The universe is full of worlds, but most worlds are not homes. That may be the hardest truth of all. The galaxy may not be empty, but it may still be almost impossible to live in. Earth is not special because it is large, not because it is close to the sun, not because it has rock beneath our feet. Earth is special because countless conditions came together in exactly the right way for life to continue for billions of years. A stable star, liquid water, atmosphere, magnetic protection, chemistry, temperature, time, and a long chain of accidents that did not destroy everything before complexity could grow. To find that again may be far harder than simply finding a planet. A new Earth may exist somewhere, but somewhere is not enough. It must be close enough to reach, safe enough to use, stable enough to last, rich enough to support life, and forgiving enough for humans. That combination may be rare, may be very rare, may be so rare that the nearest true home is not near at all. And if that is true, then interstellar travel becomes even more difficult than distance alone suggests. Because we do not just need to reach a star, we need to reach the right one, at the right time, with the right ship, carrying the right people, with enough knowledge, enough resources, enough stability, and enough luck to survive what comes after arrival. Every condition must align. And every condition adds weight to the impossible. This does not mean we should stop dreaming. Dreams have always pulled humanity forward. The moon was once unreachable. The deep ocean was once a mystery. Flight once seemed impossible, but the stars are different. Not because they are magical, because they are honest. They show us the scale of the universe without reducing it for our comfort. They remind us that not every boundary is waiting to be broken quickly. Some boundaries are not doors. Some are distances so vast that they become part of the meaning of reality. Interstellar travel may one day happen in a limited way. A probe, a signal, a machine crossing the darkness. Maybe even a tiny robotic explorer reaching Alpha Centauri and sending back the first close image of another star's planets. That would be one of the greatest achievements in human history. But the version we imagine so easily, humans travelling freely from star to star, ships moving like aircraft between suns, colonies spreading across the galaxy, that may remain beyond us for a very long time, maybe forever. And if it does, that does not make humanity small. It makes Earth more precious. Because if we cannot easily leave, then this world matters even more. Our oceans matter, our atmosphere matters, our fragile climate matters. The thin layer of life wrapped around this planet matters. Interstellar travel teaches us something by being so hard. It teaches us that Earth is not just a starting point. It may be the only true home we ever have, at least in any human timescale. We can look outward. We can study other stars. We can send instruments into the dark. But our survival still depends on this small world beneath us. A world that already gives us what no spacecraft can easily recreate. Air without machines. Water without manufacturing. Food grown under real sunlight. Gravity without rotation. Protection without armor. A sky. A horizon. A living planet. Maybe that is the final lesson hidden inside the dream of reaching the stars. The universe is vast, but habitability is rare. The stars are many, but homes are few. And the distance between them may be too great for fragile beings like us to cross in the way we imagine. So why do we keep looking up? Because the stars still matter. Even if we never reach them, they expand the mind. They show us the size of reality. They force us to think beyond one lifetime, one planet, one moment in history. They remind us that we are part of something far larger than ourselves. And maybe that is enough for now. Maybe the first true form of interstellar travel is not physical. Maybe it is knowledge, light reaching us from distant suns, signals crossing space, images captured by telescopes, equations that let us understand worlds we may never touch. In that way, part of us has already crossed the distance. Our minds have gone where our bodies cannot, and perhaps, for a long time, that is how humanity will travel between the stars, not with ships, but with imagination, with instruments, with patience, with the quiet acceptance that the universe is larger than our reach, and still worth exploring, because the stars are not waiting for us. They do not need us. They will continue burning whether we arrive or not. But we look at them anyway. We study them. We name them. We dream about them. And in that dream we discover the truth of our own limits. Interstellar travel may be physically impossible for humans as we imagine it today, not because the dream is foolish, but because the universe is real, and reality is heavier than imagination. Between us and the stars there is no wall, no locked gate, no cosmic warning sign, only distance, only time, only physics, and for now, that is enough to keep the stars forever out of reach.